Welcome everyone in lecture number 12 of Laplace transform. In this video lecture, we'll see today the Laplace transform of some special type of functions. Before starting the lecture, I would like to tell you the answers of the questions that I have stated in my last video lecture. And the first one is Laplace transform of 2 into 1 minus cos hyperbolic 2t divided by t. Its answer is log p square minus 4 divided by 4. And second question was integral cos 60 minus cos 4t divided by t. Its integral value using Laplace transform is log 2 upon 3. I hope you have obtained these answers. So let me start the lecture of today, which is Laplace transform of some special functions. So in special functions, the very first function that I would like to take is periodic function. I hope all of you are aware of periodic function. What is a periodic function? Periodic function वो function होता है जो एक interval के बाद अपनी value repeat करता है. That means a function f is said to be periodic if for some non-zero constant, if we obtained f of x plus say constant say a, its value is x, means this a after which the function is repeating its value, that is we are getting the same value as we are getting at x plus a, then this a is called the period of this function. Okay, so we can also denote the period by capital T. So if ft, here capital F t is supposed to be a periodic function, is a periodic function with period t. All the trigonometric functions, for example, are the periodic functions like sine a, sine theta, cos theta. All these are periodic functions, all the trigonometric functions. If ft is a periodic function with period t, that is f of t plus capital T is equal to ft, then Laplace of such function which is periodic having the period t, capital T, is defined as 1 upon 1 minus e to the power minus p into t. Here capital T is the period of the function, integral 0 to capital T e to the power minus p t f t dt. Okay, so this is a formula for finding the Laplace transform of a function which is periodic in nature. For example, if I would like to find the Laplace transform of the function ft, which is defined as t for the interval where t lies between 0 to c, and its value is 2c minus t, for the interval where t lies between c to 2c. Okay. So if you draw the graph of this function, we will get you may take here ft, and here we will take t. This point is 0. This point is say c, and this is say 2c. So when t lies between 0 to c, the value of the function is t. Ft is equal to t is a straight line, right? And then it is 2c minus t, means the graph is decreasing. When at c, its value is, when t is equal to c, its value is c. So it is exactly above c. And when it is 2c, the value of the function is 0. So it would be like this. So this is a graph of the function. Okay. So you can see the function is repeating its value after 2c. Okay. So the period of the function is 2c here. Here it is given in the question that period of the function is 2c here. So we solve it. We find the Laplace transform of ft, which is defined as 1 upon 1 minus e to the power minus p into t, where t, capital T, is the period. So period is 2c into p, integral 0 to capital T here. So it is 2c here, e to the power minus p t f, sorry, for 0 to 2c, function is split into two parts, so we have to put here ft, and then we split this limit from 0 to c, and then from c to 2c. So we split this integral into two parts, 1 upon 1 minus e to the power minus 2cp, 0 to c, e to the power minus p t into t dt. Let me put this in the bracket so that this value is not repeated. C to 2c e to the power minus pt, value of function is 2c minus t dt. Okay, now we solve it. Laplace transform of ft is given by 1 upon 1 minus e to the power minus 2cp. If you integrate uh, this function, so we use here product rule. So first function into integral of second function, e to the power minus pt divided by minus p, and then we differentiate first function and integrate this. This is a shortcut method. So this is e to the power minus pt over p square with the limit 0 to c plus, again shortcut method, first function, integral of second function, plus there will be minus sign, but we differentiate this with respect to t, it is -1, and integrate this with respect to t, which is minus pt over p square, c2 to c. So this is equal to 1 upon 1 minus e to the power minus 2 cp. If you put the upper limit, it will be c with negative sign whole divided by p minus e to the power minus cp at p square. At lower limit this will be 0, and this is 1 upon p square, plus at upper limit this will be 0, and this is positive e to the power minus 2 cp whole divided by p square. At lower limit it is, because of this negative sign we have positive sign here, c e to the power minus pc divided by p, and this positive sign, this lower limit, we have negative sign here at lower limit, and this will be e to the power minus pc divided by p square. You can do it by yourself. So this term cancel with this term, is 1 upon 1 minus e to the power minus 2 cp. We have this term, this, and this all have in denominator p square, and this value will get added. This is 1 minus e to the power minus 2 cp. It will be positive, and this will be negative, whole divided by p square. So this is this upper part is nothing but is the whole square of 1 minus e to the power minus pc whole divided by p square. Okay. Now this term can be written with the help of a square minus b square. It is a plus b into a minus b. So 1 plus e to the power uh, minus pc and 1 minus e to the power minus pc. Okay, that will cut one of the limit of this, one of the power of this expression. So Laplace transform of ft, which is a periodic function, is 1 upon p square into 1 minus e to the power minus pc whole divided by 1 plus e to the power minus pc. That's answer. So this is how, by using the formula for periodic function, we can find the Laplace transform of such function. You can try one more example. If ft is defined as t square for t lies between 0 to 2 and f t plus 2 is equal to ft. This is a hint that it is a periodic function with period 2. Then find Laplace of ft. Okay, this is a periodic function with period 2. It is clear here from this line. You can verify the answer. The answer of this question is 2 1 2 into 2 minus 4p square plus 4p plus 2 into e to the power minus 2p whole divided by p cube into 1 minus e to the power minus 2. You can verify this answer. Now the second special function is error function. Error function. So let me first define the error function. It is denoted by ERFT as usual. Generally we take the function as ft, but error function is denoted by ERF, error function. With here the variable is t. It is defined as 2 upon under root pi integral 0 to t e to the power minus u square du. This type of expression uh, where the limit is from 0 to t to the power minus u square du. This function is named as error function. Okay, so we find the Laplace transform of this function. Its complement uh, is denoted by ERFC. This is called the complement of the error function, and it is nothing but 1 minus ERFT. Means error function को अगर हम 1 में से minus कर दें तो that gives us the complement of error function, and it is defined as 2 upon root pi integrals t to infinity e to the power minus u square du. Okay, so let me find the Laplace transform of error function. We will prove that Laplace transform of error function is error function of under root t. It is 1 upon p under root p plus 1. Error function of square root of t. We will prove this. Prove that. So first of all, we will write the value of error function of square root of t. What is the value of error function of square root of t? You see here, error function of t is 2 upon root pi integral 0 to t to the power minus u square du. So obviously if you replace t by square root of t, what is the change here? Change is only in the limit here. Here we have the limit from 0 to square root of t only. So it is equal to 2 upon square root of pi integral 0 to square root of t e to the power minus u square du. Okay, by definition of error function. Now what we do here is we open this, we expand this function. So what is the expansion of e to the power x? 1 minus x plus x square upon factorial 2 plus x cube, right? So if we have e to the power minus x square, e to the power minus x का expansion क्या होगा? e to the power x का expansion होता है 1 plus x square upon factorial 2 plus x cube upon factorial 3 and so on. For e to the power minus x, we have 1 minus x plus x square upon factorial 2 minus x cube upon factorial 3 and so on. So here, in place of x, we replace here x by u square. So the value of e to the power minus u square will be 1 minus u square plus u raised to the power 4 divided by 2 factorial minus u raised to the power 6 whole divided by 3 factorial, okay, and so on. We put this inside the bracket and write here du. Let me draw a partition here. Okay, now this is equal to, if you integrate this function, this expression with respect to u, you will get u minus u cube upon 3 plus u5 upon 5 into factorial 2 minus u7 upon 7 into factorial 3 and so on, and we apply the limit from 0 to square root of t. This is equal to 2 upon square root of pi. When you put square root of t here, we'll get square root of t, and here we will get t raised to the power 3 upon 2 upon 3, and is t raised to the power 5 upon 2 upon 5 into factorial 2. It is t raised to the power 7 upon 2 upon 7 into factorial 3 and so on. So we have this expression. This integral has been removed. Okay. This integral has been removed. So we find now the Laplace transform of this expression. This implies Laplace transform of error function of square root of t is nothing but 2 upon square root of pi into Laplace transform of t raised to the power half. See, Laplace will go inside the bracket and it will work on each term. L of t raised to power half minus L of t raised to power 3 by 2 upon 3, okay, minus L of t raised to power 3 upon 2 whole upon 3 plus L of t raised to power 5 upon 2 whole upon 5 into factorial 2 minus L of t raised to power 7 upon 2 whole divided by 7 into factorial 3, okay, and so on. Now this is equal to 2 upon square root of pi. t raised to power half का लाप्लास क्या होगा? It will be gamma 3 by 2 gamma n plus 1. This is n. Gamma n plus 1 is 3 by 2 divided by p raised to power 3 by 2 minus this is gamma 5 by 2 divided by p raised power 5 by 2 into 3 plus gamma 7 by 2. This is by the formula of Laplace transform of t raised power n. So this is 7 by 2 p raised power 7 by 2 into 5 into 2 minus gamma 9 by 2 divided by p raised power 9 by 2 7 into 3 factorial is 6 and so on. Now gamma n is defined as gamma function मैंने आपको बताया था gamma n की वैल्यू n minus 1 फैक्टोरियल भी होती है और गामा n को आप ऐसे भी लिख सकते हो n minus 1 गामा n minus 1. अगर n एक पॉजिटिव इंटीजर है तो हम ऐसे लिख सकते हैं गामा n को, जैसे गामा 5 है, गामा 5 को आप लिख सकते हो 4 फैक्टोरियल. ओके, क्योंकि 5 एक पॉजिटिव इंटीजर है. लेकिन अगर गामा कोई और फंक्शन है, जैसे if you write here gamma 3/2, ये -1 से बड़ा है, गामा n की वैल्यू ये तब होती है when n is greater than -1, any number greater than -1, or when n is a positive integer then this. तो इसको हम लिखेंगे 1/2 गामा 1/2 इस तरह से. और गामा 1/2 की वैल्यू गामा 1/2 की वैल्यू स्क्वायर रूट ऑफ पाई होती है, ये आप याद रखिए. तो हम इस गामा 3/2 को हम इस फॉर्मूले से ओपन करेंगे 2 अपॉन स्क्वायर रूट ऑफ पाई 1/2 गामा 1/2 होल डिवाइडेड बाय ये जो p रेस पावर 3/2 है ये आप कॉमन ले सकते हो. अभी हम इसको ऐसे ही लिख देते हैं. इसको हम क्या लिखेंगे, when you subtract 1 from 5/2 it will be 3/2, गामा 3/2 आएगा. देन गामा 3/2 को हम फिर से ओपन कर सकते हैं, तो हम क्या लिखेंगे 1/2 गामा 1/2. हम तब तक ओपन करते हैं जब तक गामा 1/2 ना मिल जाए हमें, क्योंकि गामा 1/2 की वैल्यू हमें पता है, इट इज स्क्वायर रूट ऑफ पाई. It is 5/2 gamma 5/2 and then gamma 5/2 is 3/2 gamma 3/2 and gamma 3/2 is 1/2 gamma 1/2. p raised power 3 7/2 into 5 into 2. And this is 7/2 5/2 3/2 1/2 gamma 1/2 9. Okay, whole divided by p raised power 9/2 into 7 into 6 and so on. So Laplace transform of error function of square root of t will be 2 upon p raised power 3/2 कॉमन ले लेते हैं. It is इसको हम अंडर रूट पाई लिख सकते हैं. स्क्वायर रूट पाई इंटू हाफ एंड अपॉन में हमें क्या मिलेगा यहाँ से 3/2 आपने कॉमन ले लिया तो कुछ भी नहीं मिलेगा अपॉन में. इसको मैं इरेज कर देती हूँ. it will make confusion otherwise. Then minus 3/2 1/2 gamma square root of pi whole divided by p square into 3. No, it will be p only. 3 into p plus 5/2 3/2 1/2 square root of pi whole divided by p square into 5 into 2. Okay, and then negative sign 7/2 5/2 3/2 1/2 square root of pi whole divided by 7 into 6 into p cube. Okay, now it is 2 upon p raised power 3 upon 2 square root of pi will cancel all the square root of pi, so it is, you can also take 1 upon 2 common, that will make this 2 cancel with this 2. So here we'll get 1 minus 3 will cancel with this 3. 1 upon 2p will be left here. Here 5 and 5 will cancel with this 5 and we have 3 upon 8, that is 3 upon 2 raised power cube p square minus 7 will cancel with 7, it is 5 divided by 2 raised power 4 p cube and so on. So this is equal to 1 upon p raised power 3/2. This is nothing but 1 plus 1 upon p raised power minus half. Its expansion is this by binomial theorem. So this is equal to 1 upon p raised power 3/2 p upon 1 plus p raised power half. This is equal to 1 upon p. This p half will cancel with this 3/2. Only p is left. Square root of p plus 1. This is what we want to prove. Laplace transform of error function of square root of t. Based on this example, you can try the Laplace transform of error function of t into error function of 2 square root of t. You know the error function of square root of t. You can use here change of scale property, and then you can use the property of TFT. and you can find the Laplace transform of this function. So this is a problem for your practice, and its answer of this problem is 3p plus 8 whole divided by p square into p plus 4 raised to the power 3 by 2. Okay, you can try this question. You can also try this problem. Laplace transform of e to the power 3t into error function of square root of t. Here you can use first shifting theorem. Okay, the answer is 1 upon p minus 3 square root of p minus 2. This is obvious. You have to put here p minus 3 in place of p. Okay, some more special functions are still left, so I'll cover them in my next lecture. Okay, thank you very much.